So yeah, without too much further ado, I'd like to introduce Tim, VK5ZT. I've known Tim for quite a while. I think we first actually met at Friedrichshafen, from memory.
Oh, I think we met before that.
Probably before that,
somewhere
but
in
yeah.
defence.
Yeah, so we're in behind the wire.
That's it.
So anyway, Tim's talk tonight is Light Talkers, and he's going to talk about some of the fascinating experiments and developments that he's been pursuing in nanowave communication. So thank you very much, Tim.
Okay. I can hear myself. First of all, just let you know who I am, Tim Dixon, VK5ZT, licensed for almost 53 years. So I've been around a bit. And I've recently retired last year from the Department of Defence. Most of my working life has been in defence. And we play around a bit with microwaves, and this is a kind of an extension of that. So if we can have the next slide, please. This is what we're going to talk about tonight. Why do this at all? A short history of amateur optical communications. My brief history in optical communications. Optical propagation and the best options if you're going to get into this. And transmitter and receiver systems. We'll actually look at some circuit diagrams, so slightly technical. And some of my projects, which I'm certain you'll get a laugh out of. Next slide, thank you. Where's our slide man? Our slide man's gone on strike. Right, why do this at all? In the year that I was born, a man was asked, why do you want to climb Mount Everest? And his response was, because it's there. So why do you want to play around with optical? Because it's there. That's one reason. That's the kind of reason you have when you're like 16 or 17 years old and mucking around with electronics. The other thing is that optical activities are now recognized by the ARRL, the RSGB, and the WIA. In fact, the ARRL 10 gig and up contest, you can compete using optical equipment as well, and the contacts count. So it is usable. STEM, the big thing that's a flavor of the year with everyone, because they want more people in technical pursuits. And whenever we've taken optical gear along to science fairs, they've always had a lot of interest. We've had a system set up at Science Alive where we had, in a window on the far side of the hall, we had a red light being driven by a radio, and people visiting our particular display were invited to line up a little receiver on the red dot, and they were highly surprised when they got it online. Up came a radio show. So, and that impresses people. It's fairly easy to impress people with that kind of thing. The other thing, of course, which appeals to a lot of people, is cheap. It's far cheaper than radio to muck around with light, a lot cheaper. And it has a lot in common with microwave systems. So if you want to find out how microwaves are going to behave, especially higher microwaves, then light will give you a lesson. Next slide, please. This is a little bit of the history. The longest light communication, surprisingly enough, is thought to be US Army signalers using Morse on heliographs. You know, the mirrors that sight up on the sun and they flash. And they managed 295 kilometers using heliographs, which is quite amazing. No one's managed to achieve that yet. US hams built a laser in 1963, and lasers were really new in 1963. They built this huge gas laser mounted to a huge metal beam and excited by a Johnson transceiver on 28 megahertz to force the gas in the laser to ionize. Crazy, but it worked, and they managed a voice transmission over 190 kilometers. Now we get to Australia. In 2005, VK3AML and 7MJ achieved two-way voice over 167 kilometers, and that's from the top to the bottom of Tasmania. That was from top of Mount Wellington and firing north to another mountain. And that, at the time, was an Australian record and was actually the world record for optical communications. And those guys are still around playing with this stuff. And then in America, KA7OEI and friends exceeded that range in 2007, taking it out to 172 kilometres, and have also achieved a one-way, just an MCW exchange over 278 kilometres. They still haven't equalled the Army signal as yet, but they're quite amazing ranges for optical equipment. Next slide, please. A little bit more history, and this is where I sort of dialed myself back into it. From 2006 to 2008, VK7MO, Rex, and 7TW, Justin, managed to do some non-line of sight signals using weak signal detection techniques. And this was across Bass Strait by shining the signal up towards light clouds. They call it cloud bounce, but it isn't really. It's more like cloud diffraction. The beams get bent back down towards the Earth. But it was a digital mode, and it was those sort of things where you turn on the receiver and you set it going, you go away and make a coffee, have your lunch, come back and look at the log and see whether it managed to dig anything out of the noise. So, yeah, it worked, but not practical for sort of normal communications. In the UK hams have their voice record there is 129 kilometres. The UK is a bit like here, it's fairly flat. If you want a line of sight path, it's very hard to find one that's longer than 130 odd kilometres because there's no really high mountains. And there's some guys there doing some work with non-line of sight stuff. Some guys are sending low bandwidth digital television transmissions across light beams. The Germans are doing that, and the English guys are doing that. And as you can see in green, biggest problem around the place if you want really long distances, lack of high places. Next slide. Now for me, I scraped the paint off of an OC71. You're all saying, what's an OC71? Well, if you've been around for a long time, you remember that in the 1960s, you couldn't buy many semiconductors anywhere. There were no Dick Smiths or J-Cars or anything like that. And one of the most commonly available transistors in the 1960s, the late 1960s, was the OC71.
Come on.
A point contact germanium transistor. And Mullard sold two versions of that. They sold the OC71 and the OCP71. The OCP71, as depicted there, had a clear case. The OC71 had a black case. Didn't take long for people to realise if you bought the black case one and scraped the paint off, you had an OCP71. And of course, Mullard charged 3 times as much for the OCP71, so everyone was scraping the paint off the OC71s to make light-sensitive transistors. Mullard woke up to that after a while, and that material that's inside the glass case, they converted that to a blue opaque material, so you couldn't use the standard OC71 for optics anymore. Now, when I saw VK7's lecture at Gibbs Tech, way back when, 2009, I thought, wow, because I've been going to Gibbs Tech for a long time, and for the microwave side of the house, and I thought, wow, I need to get back into that. I used to do it when I was a geek years ago, and I thought I could get back into that stuff. The next slide. So I did. And the year that stands out in all of this is 2017. In 2017, as a result of a large amount of travel for work, I became a gold card Velocity card holder on Virgin Airlines, which meant I had a doubled baggage allowance on Virgin and partner airlines. Now that matters because that year we managed to get Peter Freeman to move Gibbs Tech forward to the 1st of July. Then on the 8th of July was the Finningley Microwave Roundtable in Doncaster in Yorkshire. And then the 15th of July was Friedrichshafen. So my plan was depart on the 30th of June, fly to Melbourne, go to Gipstech, displayed all the optical gear, which was packed in my second bag that I was able to take along with microwave gear, 10 gigs and 47 gigs, and all the accoutrements that go with that. So I went to Gipstech, gave a display, and then as soon as I got out of Gipstech, back down to the airport, flew to London, went up to Doncaster via Bletchley Park, of course, as you do, and in Doncaster went to the Finningley Round Table. And at the Finningley Round Table has a group of optical enthusiasts, and they had an interesting talk there I wanted to see on an optical transceiver they were building that used a large light-emitting diode as both the transmitter and the receiver, because LEDs will work as detectors of signals as well. They're not as good as purpose-built ones, but they will work. And Finningley's people had happened upon a specific brand of LED that worked fairly well. So I wanted to see that particular display. And while I was there was a guy demonstrating some optical gear. And he was set up on a table, and about 100 meters away, there was another guy with a Fresnel lensed optical receiver. And he was pointed at this guy, and the two were chatting on. And I said, I have some optical stuff with me. And he just looked at me thinking, you're a mad Australian, you know, you've dragged all this stuff halfway around the world. And I said, well, yeah. I said, I'll set it up. And I set the gear up, and I pointed it at the guy on the other side of the car park. And because he's using a Fresnel lens, and the guy next to me was beaming at this lens, and the light that was hitting the lens was bouncing back. And I was hearing his voice on the reflected light from the front of his system. And I said, the guy next to me, it was Barry, I think, and I said, I can hear you coming back from the reflection off the front of that system. And boy, that guy was quick-witted, because he pipes up and he gets on the microphone, he says to the guy at the other end, oi, you need to do some more work on your transceiver. You're getting too much reflected power. Because that just broke everyone up. It was quite funny. So we had a bit of fun there with those guys, and then flew to Friedrichshafen the following Monday. That was the one small fly in the ointment of my travel arrangements. While I had double baggage allowance on Virgin Airlines and all its associates, I didn't have it for Lufthansa. So when I rocked up to check in this luggage, oh, that's going to cost you an extra €100 for that. Okay. So I had to fork out a chunk of money to ship this box full of radios across to Germany. Now, while we were in Germany, I went to a talk there, and this guy, of course, the talk was in German, which was a major impediment to my understanding what was going on. All I could do was look at the pictures and try and guess what he was talking about. And he's talking about these LEDs and these fabulous optical systems they had. I don't know where they got their optical systems from, but they were great, you know, super duper lenses and all sorts. And they said they were getting 40 kilometers. And I'm thinking, 40 kilometers, that's nothing. You could do that with a torch. And then I woke out, yes, they were getting 40 kilometers using a normal LED in daylight. Now go figure how they did that, because that's hard. Anyway, while I was there, one of the other guys I was with made contact with a German amateur and mentioned that I had all this optical stuff with me. Straight away, this guy's, yes, we have a contact. And I got his phone number and I rang him up. His name was Klaus. And he says, yes, we have a contact. Let's go out tonight. And I said, well, okay. And he was just outside Friedrichshafen on a hill. And I was somewhat west of there on the side of another hill. And we were 44 kilometers apart. And he said, oh, by the way, my system is infrared. And I said, oh, it's a little bit hard to see infrared light on the horizon. And I said, well, my system will work at infrared because the BPW34 photodiode is fine at infrared. But I need to find you. And we're on 2-meter handhelds. And by this stage, I'm ensconced in this sort of hotel restaurant on the side of this mountain in Austria, because Austria is not far from Friedrichshafen. And the hotel staff are wondering what I'm doing under their back veranda with all this batteries and lights and stuff set up, talking to this guy in Friedrichshafen. And he says, I had a pair of binoculars with me. So he says, I'll wave a torch. Okay. So I'm looking through the binoculars and I spot this little twinkle, and I found you. So turn my system on. And of course, sighting up on him was pretty easy, because when you turn on a very powerful red beam that spears out into the night, it's pretty easy to see where it's going. So I line up on him, and straight away he comes back on 2 meters. And he says, wow, he says, you're the strongest light on the horizon. I said, I'm not surprised, considering the power of this system. So I cranked the power back, and we had quite a long chat. That, as far as I'm aware, and I haven't seen anything to the contrary, it's probably the first amateur communication between 2 different countries. Because everyone else you read about is in America or England or Germany, but you never see anyone talking across border. So here we have a German at Friedrichshafen and an Australian in Austria making the first international optical contact, unless someone can prove otherwise. We were still roaming around Austria for a while, and Dave 5KK and Ian 5ZT were both at a place called Scharfberg. Scharfberg is a big hotel restaurant complex on the top of a mountain. They were there for a couple of days prior to driving back down to Munich to fly home, and I was in Austria for another week. So I'd driven north, and I was on a hill in what they call Upper Austria, and we've been testing some 10 gig stuff back to Scharfberg and 47 gigs. And I said, I'll turn the optical transmitter on and you see if you can see it. And I'll try and look, because I know roughly where they were on the horizon. Moved it around. Finally, Ian came back and said, yeah, no problem. We can see a bright red light on the horizon. That's over 60 kilometers away. And of course, he couldn't do anything about talking to me because he didn't have any equipment with him, but he could see me. Anyway, that kind of boosted Ian's enthusiasm, and he'd been slowly building some gear. Well, as soon as he got back, he furiously built all the rest of his gear. And then we went out up north and created the first South Australian optical record and the first digital optical record, which is the Australian optical record using digital communications. We did that in late 2017. Next slide, thanks. All right, enough of the shenanigans of me roaming around Europe and whatever. Let's talk a little bit about the nitty-gritty of how all this works and what are the enemies of propagation. First thing's alignment. You're in deep trouble if you don't know where the other person is on the horizon, and at night time, it's very hard to find them. So before you do anything, you need to establish exactly where you are on the map, where the other station is on the map, and exactly what bearing they are from you. Otherwise, you'll be searching for a long time. And that's one of the big problems if you're enthusiastic enough to use lasers, because lasers are even worse than the systems we use to try and find at the other end. Then you've got the losses along the way. And the biggest enemy of lasers, and why almost no one uses them, is scintillation. Scintillation is small pockets of gases in the atmosphere that they're like little cells, and there's a lot of them. And as the light travels through one of these pockets, it's changing from a more dense to a less dense medium. It will move slightly. Doesn't take much, especially when you're going through 100 kilometers of them. And what that does is it makes a tremendous mess of the beam. You get a lot of attenuation, a lot of flutter, and it makes lasers hard to use. You find that the systems that we tend to use have quite large beams, either a big beam from a Fresnel lens, or in my case, I use a 100mm glass lens. The next loss is scatter, which is sort of related to scintillation. Scatter is what makes the sky blue and the sunsets red. because it really hammers the shorter wavelengths like blue and violet. So that's why optical communications almost invariably do not use blue or violet, because the atmosphere will destroy it. So you're down at the red end of the spectrum and the infrared end of the spectrum for best results. Red and IR, obviously favored. The other thing is absorption. You've got to be awfully unlucky with absorption, but the molecules of the gases in the atmosphere have spikes of absorption across the light spectrum. If your optical system just happens to be sitting on one of those really deep spikes, then you might struggle a bit because the gases along the way will be absorbing your beam. Hard to know how to deal with that because half the time you never know what wavelength you're actually on. So you just have to keep your fingers crossed. Next slide, thanks. And this is the sorts of things that are being used for optical communications. LEDs, normal red LEDs. Nowadays you can buy some pretty bright red LEDs, just 10mm LEDs, high brightness LEDs, very little current, but very bright. And you get very good results with those. And of course, Luxian LEDs came out about 20 odd years ago, 20 plus years ago. And they're even brighter, up to 5 watts of input. Lasers, well, you know, I've already told you about lasers. They're a struggle to use, but I've tried it. And the real king of them all, photonic lattice LEDs or flat lights. These are beasts. These things are used in these sorts of things, projectors, and red, green, and blue. And they have massive output power. I have 2 different sized ones. The bigger one that I've got will run a standing current of 35 amps. 35 amps through a bank of LEDs generates a very large amount of light, far more than you need most of the time. And I've got a smaller size one, a mere 20 amp one, which we use in the normal system, and we usually throttle that back because just in the interest of power efficiency. Now you've got to modulate it somehow, and there's a few ways of doing that. Baseband AM, that doesn't work with lasers because of the way lasers initiate the beam. Varying the current through a laser doesn't work out very well. But it certainly works fine with LEDs. So you simply modulate the LED with plain old audio, and you drive it as hard as you can from rail to rail. You can let it clip top and bottom, doesn't make much difference. And that's probably the most basic system and the easiest system to get on the air, and works fine. Next, pulse width modulation, which does work with lasers, where you simply, it is what it says it is, vary the pulse widths of turning the LED or the light on and off. Works very well. Receivers don't need to be anything special because the receivers, with the pulse width, the frequency of the pulses, it almost invariably can't make it through the receiver. So what the receiver ends up doing is just producing the baseband output and pruning off the high frequency component. So the receivers still work fine. And a system popular in England is subcarrier. You build a down converter to 20 kilohertz, say, connect it to an FT817, modulate the LED with the 20 kilohertz signal, and that gives you FM, AM, SSB, all on the beam. And you do the same thing the other end. You try and recover that signal. And the English guys swear by it. And yeah, it's gives a much more amateur radio feel to operating because you're sitting there with an FT817, you know. But the problem you have is, I think they sacrifice something in doing that, because getting your optical system to produce an optimal response at, say, 20 kilohertz is actually quite difficult. But they seem to like it. And considering the distances that they're limited to going over, that's probably fine. Next slide, thanks. Here we are, a circuit diagram. I'll just get my exceedingly powerful laser pointer, which I won't point at you guys. This is a very simple transmitter. You look at that up there. There's the audio amplifier, microphone audio amp, gain control. Down here is the DC bias set. The LED is right there. It's a power MOSFET there, and it's got this little current feedback arrangement here, which enables you to smoothly control the MOSFET by looking at how much current's flowing through this resistor. That works very well. You just set your idling current for the LED there and feed audio in there, and you get modulated light coming out of there. And that's one IC, an LM324. That says there, don't substitute, because an LM324 will allow you to go from rail to rail. You can go down virtually to 0 volts, sort of full supply voltage. You got next to nothing in it: a power MOSFET, a LED, one IC, handful of components, 5-volt regulator to set this DC setup here, an electret mic, and that works fine. That's courtesy of KS7OEI. He's got a number of designs on his website. This is probably the simplest one. He's got a few others designed around higher power LEDs. But that's as easy. I mean, that's an afternoon's work to put that together, and you're on the air. And then you've got to build the optics to go with it. And next slide, please. Now the receivers. Receiver considerations are a lot like any receiver, really. You're looking at low noise designs. All the transistors in the system or the ICs, you need to be low noise, because you are right down in the noise coming out of these receivers, and you get a lot of noise out of them, and I'll demonstrate in a minute. They need to be well screened and have a lot of RF bypassing. And you'll say, well, why? That's simple. You're stood next to an optical transceiver here, holding a 2-meter handheld. And as soon as you push the transmit button, if you haven't got fairly reasonable bypassing in all the high gain audio circuits that you're standing next to, then the 2 meters just goes straight in there and upsets things quite dramatically. And the first evidence I saw of that one day was I had the transmitter on, pushed the transmit button, and the light output doubled from the system because it changed the biasing on the LED. So we quickly whipped out a pack of 0.01 mic caps and sprinkled them liberally through the circuit to try and keep the RF out of the electronics. You can buy optical filters for many wavelengths. So if you happen to know the frequency of your transmitting LED, or the wavelength more than frequency, I don't usually use frequency. If you happen to know the wavelength, you could buy a filter for that wavelength and put it in front of your receiver and get rid of everything else that's out there other than background light, that particular component of white light, or your transmitter. Haven't really tried that, but I know other people have. Generally speaking, the receivers we power them from batteries like 9-volt batteries or 12-volt batteries. If you try and power it from the same power supply as the transmitter, if you turn them both on at the same time, and you have a transmitter that might want to pull 10 amps out of the power supply rail, which might be a battery sitting on the back of your car, you're asking for trouble, because that will find its way into the receiver supply. And yeah, so generally battery power the receivers, and then you need bigger batteries to power the transmitters. What sensors are we going to use? Photodiodes mainly, BPW34, red and infrared sensitive. That's what I use in most of the systems. LEDs in reverse, as I mentioned, the Finningley Amateur Radio Club design. LEDs around backwards. They work. Avalanche photodiodes. Interesting devices. You can find them around the place. They are expensive. The cheap ones tend to be on completely the wrong frequencies, wrong wavelengths. But there is a new breed of them out now that are being used in LiDARs, in cars and other things. Again, probably not on the frequency we need to be using. Expensive. interesting. I've got one. You have a trade-off between noise and sensitivity when you're using them. I haven't seen any great advantage in using the one I've got. And of course, the king of photosensitive devices still, after many, many years, since photomultipliers have been around since the 1950s, but they are the best in terms of optical sensitivity. They're a little bit fussy to use because they typically need a 1,000-volt power supply to run them. But if you can get past that hurdle, they've got quite wide bandwidths, and they are sensitive down to the photon level. A well set up photomultiplier system in the right circumstances could detect the arrival of a handful of photons, which is sensitive. The one that I have at the voltage that I'm running it at has a gain of 1 million. That is a lot, right? And it is unmanageable at that gain level because anything but any light source anywhere nearby gets into it. So I got work to do on my system. Fortunately, the gain of photomultiplier tubes linearly tracks the voltage down, so you can half the supply voltage and knock the gain back quite a lot, which is the plan for mine. We'll talk about mine a little bit later on. Next slide, thanks. Receivers, typical receivers. Now, you could build a really, really simple one. Look at that one there. 2 transistors, a photodiode, handful of components, the K3 PGP receiver, very sensitive. Does work. That's a nighttime only version. This is KA7 OEI's design, the other one, and it is very good. It has options up here for filtering the output, varying the gain. The strange thing you'll notice about these things, I mean, have a look at that lead and that photo transistor and that FET. Look at that biasing arrangement there. Isn't that weird? It's exactly the same here. The gate of the FET connected straight to the photodiode. Not only is it connected straight to the photodiode, but you can't read that blurry note. That connection has to be made in air. You do not put either of the leads of those components through the circuit board. 2 things will happen if you do. 1, you'll increase the capacitance of the leads, the surrounding components. And 2, you may get some leakage across the circuit board. Because with that being a MOSFET, with nothing else connected to it, the circuit impedance at that point is approaching 100 megohms, which is why you have a problem sometimes with the bandwidth of these receivers. This has got an interesting arrangement. If you look at the cathode of that lead, you'll see it goes up via a resistor chain to the supply. What that does is it makes sure that that diode is reverse biased, and it widens out the PN junction, the gap. You know what varicap diodes are? All diodes are varicaps in one form or another. That positive voltage widens out the gap in the diode to reduce the capacitance across the diode. Because if you remember back when you was in your studying days, you would have studied RC time constants. And that's the time taken for a capacitor to charge to 66% of the voltage supplied by a resistor, which sets the frequency response of an RC network. Now, when the R bit of the RC network is 100 megohms, how much capacitance do you think you need before the frequency response of that circuit is like 0 hertz or 1 or 2 hertz? The answer is not much. So you can't have very much capacitance in there, otherwise you'll deafen the front end by knocking its response right down. And as it is, that there is probably good. It's starting to fall off at about 1 kilohertz. So it's not, and this is where I kind of question the English approach, where they want to get 20 kilohertz signal through an RC circuit, which is rolling off quite dramatic at 20 kilohertz. I'm guessing they probably make up for it with gain further along in the circuit or a different sort of front end. But anyway, very good circuit though. Highly recommended if you want to build a receiver to build that circuit there. Readily obtainable bits. You can buy just about everything from JCar. It won't take you long to build. Next slide, thanks. And if you build it, you need to test it. It's pretty hard knowing what you're doing without at least having some rudimentary test equipment. Multimeter and a crow are useful to have a look at waveforms, working out how hard you're driving the lead, that sort of thing. So I built a couple of bits of test gear. The first one's called the black hole. Bit of pipe about this long. And there's a hole in one end where you clamp the receivers over with a black foam to keep light out. The other end, there's just a lead being driven by an NE555 with an 800 odd hertz tone. And you can vary the brightness of the lead with the pot, so you can create a really weak signal in a very dark environment. And that at least gives you a way of comparing receivers to say, well, if the new is this new receiver better than the old one or whatever. And the other is what I call the multi-mode beacon. We can have the next slide up. There they are. That's the black hole, that big black thing. And the other thing is the multi-mode beacon, which is this. Switch this on, and it generates a signal. Now you just see that as a red lead, but in fact, it's pulse width modulated with a tone. Next, there's also a lead on the side, which is the weak signal lead. If you need a really weak signal, you use the lead on the side. This switch decides which of these is turned on, so we turn that one off, and we switch this one on, and we get a laser. I won't point it at the camera. So we get a laser. That's useful if you're setting up your system and you need a signal a long way away. You can either go a long way away and put a signal there and hope no one steals it while you're back at where the receiver is, or you can point the laser and illuminate something a long way away with the red dot, and then that's your signal that you're looking for to test your receiver. Again, all three LEDs are pulse width modulated, and they are actually, I can give you a quick lesson to them. That noise, that's these fluoros. The light level in here is completely hammering that receiver sitting on top of the box. So we just get hum. We turn this on. Put it back to the start. So that's what it's actually sending. It's a pulse width modulated signal. My call sign and sending CQ. So that's how that works. And that provides me with a number of signal sources to help with testing. Very handy in the early stages of working on the system. Right, well, there we are. You see the little laser, 10 millimeter lead, and the little lead on the side is the very weak signal. You sit that on the fence on the other side of the yard, you can barely see it. And if your system can see it, then you know you're doing well. Okay, next slide, thanks. All right, now for the funny part. Some of my systems, I think I mentioned at the start that I spent an awfully long time working for a government department, either on the contractor side or for them, which is an environment full of acronyms and projects. So naturally, my projects have names. Here we are. The sewer pipes. Let's go to the next slide. Thanks. This is the system I use most of the time. I was roaming around Cheapest Chips one day, and I spotted these nice magnifying glasses hanging up. They were $2.50 at the time. They're probably $5 by now. About 100 mil in diameter. I thought, oh, that'll do. I'll have one of those. Focal length about this long, so I'll have one of them. We also found some Fresnel lenses. We'll talk about those in a minute as well. I found that lens was an interference fitting a piece of sewer pipe. And so I bought two of them, built two identical pipes, receiver in one and the transmitter flat light in the other. So we'll go to the next slide. And there it is. Modulator up the top here. Receivers, that's the receiver there on the back of the receiving pipe, and that goes away to an amplifier. That there is the flat light heatsink, because they need heat sinks, and it's turned on there. You've got a red light. That controls how much audio you feed to it and the actual optical level. So you can crank it right down to just a glimmer. And surprisingly enough, even that works fairly well over most distances. So that's the system that we've used a lot. In fact, that system, we took to Mount Lofty. That went to England with me, by the way. That was what was in my big bag, right? We also took it to Mount Lofty when we were testing some 10 gig and 47 gig stuff. And VK5ZT was 150 kilometers north of us in the wind farm north of Snowtown, up above Lakeview. There's a Telstra microwave installation up there, and he was there. We'd done the microwave testing, and it got dark, and I said, turn your optical transmitter on. Let's see. The problem Ian had was that wind farms are where they are for a reason. And he was in a howling gale trying to hold down this big Fresnel lens box and keep it pointed at Mount Lofty where I was. And after about, I don't know, half an hour of searching with binoculars, I finally saw this faint red glimmer on the horizon, in amongst all the other lights that was there. Swung this thing around, lined it up, and I could hear Ian counting. 1, 2, 3, 4. He was fluttering all over the place because he was wrestling with the wind. But I could hear him counting up. And I thought, wow, there's 150 kilometers there. It's a pity we couldn't find a better site to get more distance. So we have managed a one-way 150 kilometer length. And the rule of thumb is simple. If you can physically see the red light at all, then your optical receiver should be able to hear it. Next slide, thanks. Fresnel lenses. Now, these are very popular. The English people use them, and they're popular, I guess, primarily because they're big. They're like this. So you've got a bigger capture area for the light. You can gather more light. That's fine, except that they don't focus like to a dot, almost like a lens does usually, like a glass lens. They focus down to something called a blur circle, which is like a round fuzzy dot. So you may or may not get all the light you're receiving onto your photo detector. But Ian uses one. His seems to work fine. I got the Fresnel lenses from Cheapest Chips, same place as the magnifying glass. They sell them as page magnifiers for half-blind people to use to magnify books to read. So I bought a few of those. We also went down to the picture frame section and bought some A4 picture frames, knocked them apart, threw most of them away except for the sheet of glass, which were glued to the front of the lens to protect the ribs of the lens, because the rib side of the lens is what faces the target, and if you get them filled with dirt or scratch them or whatever, you degrade. So we cover them with a sheet of glass to protect them. The transmitter side, and this is an issue no matter what system you're building, the flat lights, a flat light LED by itself has what's called a Lambertian distribution. In other words, it's sort of like that. The light coming out of it's that kind of shape. In other words, it's all over the place. If your lens is just here, you've sacrificed everything that's off to the side. Luckily for us, flat lights that I got came with a thing called a plano convex lens already bolted to the front of the flat light. The plano convex lens brings the beams in to be much narrower. So when the flat light's in the box illuminating the Fresnel lens, most of the light hits it. You get a pretty good output. Next slide, thanks. There it is. Much more powerful modulator on this one. That's two 5-volt buck boost type supplies in parallel to give me a lot of current to run a very powerful flat light. It's pretty bright. That's the transmitter, obviously. There's a receiver, and the perils of dragging these things around in the back of the van. There's a big crack in the glass that coats the front of the lens. That works. I don't think it's radically better or worse than just the glass lens system, but we have it anyway. So that's the system that a lot of people use, but it's a lot of work making all of that, making the box and then getting it away. Cutting up a piece of sewer pipe and putting a lens in one end and a cap on the other was far quicker and easier. Anyway, next slide, thanks. Thick beam laser. I mentioned that lasers have their pitfalls. I don't know whether it was a fit of madness or inspiration, I decided that if a normal laser, like a laser pointer, you got this tiny dot that's got to make it through 50 kilometers of atmosphere, and it's getting hammered by the scintillation effects. Why not start with a bigger dot? So I bought this laser, which is what they call a thick beam laser. That dot's actually more like about 10 millimeters across. So I figured this will probably be less susceptible to scintillation, perhaps, than a thin laser. There's a picture of it. And these little controls here give you some idea of the complexity of trying to aim a laser. You need to be making really tiny adjustments of where the laser's pointed. So I did that by threaded shafts and springs, which allow me to just move the laser over very small increments to get it lined up. I've only had Ian see this once in an experiment, and he said it was as easily as bright as all the other stuff I've been using, as you'd expect it would be. We're only over about a 10-kilometer path. Pulse width modulator, there's a microphone on the back of this. Won't turn it on again. Its power output can be up to 200 milliwatts. It's a reasonably big laser for mucking around with at home. It's actually a class 3B device. And at 200 milliwatts, that puts you in danger of almost instantaneous eye damage if you happen to get it in the face. So look at the back of your eyeballs running at full power. So I've got this one throttled back somewhat. It's pulse width modulated for a start, so it's actually off half the time. And its average power is sort of under 100 milliwatts. But at full power, we're only shining this thing around the place too much. And we go back to the slide, we'll have a comment on something I said there. Use that a couple of times. We may try it again. Note in red, some care to avoid being arrested is also needed, because when we were at Mount Lofty, I couldn't turn my system on to try for a contact with Ian, although he could probably have tried to listen, because as I was looking at Ian, down on the plains in front of me was Parafield Aerodrome, and in the line of sight was aircraft on approach to Parafield Aerodrome. Now, what do you think would happen if I turned on this insanely bright red light and speared it through the airspace above Parafield Aerodrome? Well, the first pilot that saw it would say, "What is this?" And if I'd have done it with a laser, it would be even worse. But so going from Mount Lofty up north can be fraught with difficulties, because you can't just go firing highly powerful red light beams over the top of the city. And I could see the aircraft flying right where I was going to fire the beam, and I thought, nah, we won't turn this one on while we're up here. And yeah, as I said there as well, alignment's problematic. You saw the little very, very fine alignment method I use on that one. We will try some more experiments with that, but I say a certain amount of care is needed because you hit someone in the face, yeah. Class 3B lasers go up to 500 milliwatts, and that's only 200 tops, and I'm running it at less than that. So the risk is lower, but there is still a risk, much more so than the laser pointer. Okay, next slide, please. That's a picture of that unit. We've already seen it on camera. That's it turned on top of it. It's got a little mounting plate on the top of the main sewer pipe system. And it's got a very strong set of magnets on the bottom of it that lock it on the plate so that you can point it. Okay, we'll go to the next slide. Moving right along. The Optigun, my favorite one. When I saw what Finningley Amateur Radio Club have been doing with bi-directional systems using LEDs, I thought, yeah, we can build one of those. One evening, I got all enthusiastic, came up with my own version, and it uses a mobile phone handset. And you never leave it in checked luggage when you're going onto a plane, unless you want a very long discussion with security. And what this is, turn it on at the moment, is a single LED. Let's make a mess of these knots. A single LED used for both transmit and receive. If I can get the wires off of the device. You'll see what the lens shows up when we turn it on. I didn't bring an extra set of plugs, so we can't plug the receiver in at the same time. But when I turn that on, you can see that that's focused. You can see the dye of the lead that's in there. And that's modulated by speaking into this. The tone on. We hear that weak beep. You press a button on this headset thing, you can see the LEDs modulating with the tone. When you speak into that, the audio goes out. When you're back the other way, you got the headset on, you can hear the received audio. So this is, I wouldn't call it a long-range device. It's an interesting toy to play around with and to give you a quick listen to see what's going on with your system as well. But like I said, you wouldn't want to have one in checked luggage going onto a plane. So the electronics in that are a bit rough, but that proves the principle that you can use a big 10mm LED for both the transmitter and the receiver, because that just uses the one LED. Next slide, it's just a picture of that. We've just seen it. Okay, next, Project Halo. Now, this is a bit nutty, this one. High aperture laser optics, that's where the name Halo comes from. Reasoning that if one laser is overly affected by scintillation, then 8 will be less so. So we built a kind of a diversity transmitter. Pointing 8 lasers at a spot 50 kilometers away, when they're mounted in a piece of MDF and held in place with hot melt glue, really doesn't work. So the best I could expect was to point all the lasers in the approximate general direction, roughly parallel to each other. The rationale being that if there's 8 beams headed that way, all right, you might struggle to find one, but if there's 8 of them, you've got 8 times as good a probability of finding one of them. Next slide, thanks. And there it is. The 8 LEDs are around the outside, the halo, and the receivers are cut down Fresnel lens, and the receiver's at the back of that piece of tube, and there's a pulse width modulator down there that drives all the lasers. So that, wow, yeah, that was slightly on the crazy side, but it'll probably work. I've never tried it. We need to get out in the field and see whether it gives us any greater chance of seeing a laser over any greater distance. That's Project Halo. And now for the granddaddy of them all. Next slide. Project GORT. Giant optical receiver transmitter. Project GORT, I had this 50-inch television in my junk box. Dead electronics, projection TV, big mirror in the back. And I took it apart and I found out of the 3 bits of plastic that made up the screen, one of them was a giant Fresnel lens, and a very well-made one. I thought, whoa, here we go. Measured it up down to the local sign writing shop and said, cut me a piece of 3mm polycarbonate sheet this big, because the lens was really flexible. Glued the lens to the polycarbonate sheet and got my stepson to grab the other side of it. Sunny day, sun overhead, piece of pine offcut on the ground. Walked outside with this big lens, pointed at the pine offcut, which promptly burst into flames. Virtually immediately. No waiting for that fire. It happened straight away. And you do a little bit of thinking. I reckon radiation hitting the surface of the Earth is around 1 kilowatt per square meter. And that lens is around a square meter. We were putting 1 kilowatt of power into a spot about that big, which meant the wood didn't withstand that for very long. In fact, it was fire immediately. I couldn't believe it. I thought it might smoke. If it didn't, it flames, smoke straight away. I thought, whoa. Which brings me to another problem that you have with these systems. If you've got a Fresnel box sitting in the back of your car and you're driving around on a sunny afternoon towards wherever you're going to do your test, and the sun hasn't gone down yet, but it's nice and low on the horizon, and you happen to turn around such that the sun shines into the back of your car and hits your Fresnel lens and promptly toasts the inside of the box for you, burns up your electronics, and if you're really unlucky, sets the box on fire. And if you want to find out how that happens, ask Ian, 5ZT. Because Ian was testing a system in his backyard, Fresnel lenses. Ian's house, his driveway faces west. The sun was going down and had just gone between his carport roof and his fence, front fence. He was out where the targeting system was, and he looked back to see the smoke rising out of the receiver as the sun was promptly burning a patch of the back of the box. Luckily, it didn't hit the BPW34, otherwise it would have probably melted. This thing is way worse. So I can't take it anywhere, and I've taken it out a couple of times. I have to keep it wrapped in stuff all the time because any sunlight in the back of that and the box will be on fire. I won't have any second chances or I'll wreck the electronics. What I'm trying with this system is I reasoned that blue light scatters more than red light does. And I decided that I wanted to try a non-line of sight path by firing a very powerful blue light beam out towards the horizon and have this thing at the other end listening for that light beam, but non-line of sight. Let's go to the next slide so we can see what it looks like. There it is. It's not exactly portable, all that portable. It has to be on a trailer if you're going to take it anywhere. The blue thing there is the transmitter blue light. Story about that in a minute. The box down below is a photo multiplier tube and power supply in a little box. The power supply is smaller than the photo multiplier tube, and yet its output's nearly 1,000 volts because the tube only needs less than 1 milliamp. So that's all self-contained. There's black tape over the end because photo multiplier tubes, when exposed to the bright light, can suffer permanent and irreversible damage. so need to be kept away from bright lights if possible. The only way I can turn that on and have it be really quiet is to plonk it face down on the table, because even with all that black tape over the end, a photon or two manages to sneak through and you can hear them on the tube. And that's what it's like. Now, use your imagination here a little bit. Photomultiplier tube with a gain of 1 million inside a Fresnel lens, which is probably about as big as you're going to be able to build as an amateur radio operator with Lord knows what optical gain. What you have here is a system that is right out and beyond the cutting edge of system sensitivity. The overall gain of this system will be astronomical. In fact, it will be unusably so. Stars will overload this. So I'll probably have to throttle back the photomultiplier tube quite a lot to do the experiments, because you couldn't turn it on anywhere near the city because of the light spillage from the street lights. You have to be way up north in a dark spot, not looking back towards Adelaide. I'd have to be facing north on a moonless night, because the moon will overload it. And my guess is the stars probably will too. So it will need to be wound back to be usable. Otherwise, the noise out of the system would drive you nuts. That blue light there, I've got it throttled back with a nice little idling current of probably 100 or 200 milliamps tops. That light is a high power one, can handle 35 amps. One night when I was experimenting with that system, I sat on the bench and I inadvertently applied full power to the blue light. I couldn't see for maybe a minute or two. I turned it off, but I can't see anything. Literally, I could not see anything. And I thought, sugar, have I done myself some permanent eye damage here? And I sort of waited for a while and looked around, and there's this shape in front of my sight as I'm looking around the room, and I'm thinking, well, I think I'm getting better. After about 20 minutes, I was kind of back to normal. That's the kind of light intensity we're dealing with. It's like a welding flash on steroids. And like I say, it blinded me temporarily when I did it, and it scared the crap out of me. So, you got to be, I couldn't believe it. It just, so that's what I'm planning on using as the beam source for the non-line of sight experiment. Again, it's a kind of a round to it project, because a fair amount of logistics required to get all this out in the field. I've still got this. There's behind that Fresnel lens, there's a big mirror that directs all the light down into the base, where there's a hole where the lens system for the TV tubes was. And those lenses focus all that light down to a dot. And you can imagine that dot would be not dissimilar to the dot on a scanned television tube. So a very small dot. So the photomultiplier tube, the face is about 25 mil across. So all the light that sees will be on the photomultiplier tube. So I really don't know how that's going to behave and whether it's going to be unmanageable out in the field, but it certainly won't be lacking in gain. So that's Project Gort. That's still all parked in the shed at the moment, waiting for an opportunity to do more with it. Okay, next slide. That's, the Wireless Institute must have been paying attention, because they gave me one of these. So for work on microwaves and optical equipment. 2018 was when I gave a talk at the Wireless Institute. I gave this particular talk at the Wireless Institute convention. And the next slide, thanks. Thanks for listening. And there's some sites to go and have a look at. Modulatedlight.org. That'll point you away in a number of directions, especially the Clint site, which is really interesting reading. In March 2019, Barry Chambers gave a lecture on amateur optical communications. Covers a lot of the territory I've covered. There's also a YouTube presentation by VK3AML, relatively recent, only went up last year. And the UK Nanowave group, groups.io, UK Nanowaves, and that's just guys chatting on about the things that they're doing. I'm pretty sure there are some German sites as well, but pretty hard to find. And those, if you're at all interested in any of this or the history and what people have done, you'll find links all over the place out of modulatedlight.org. Okay, next slide. We're done. Thank you very much for listening.
Thank you very much, Tim. Fantastic talk. And hopefully it spurs some ideas. Has anyone got any questions? Peter.
Good evening, everybody. Excuse me, bit of a throat. With the gun, where you have a two-way contact, is it talk, receive, talk, receive?
Yeah,
Is it full duplex?
No, it's not full. You can't do full duplex with
That's
one
what
diode.
I thought, hello.
No, there's a switch on the bottom of that thing that I used to turn on the transmitter.
Okay.
So you switch on the light for transmit, turn it off for receive.
Could you then make a full duplex pair by having blue in one direction, red in the other?
You could. You could probably make a duplex pair just using two red lights, but just shield them from each other.
Oh, yeah.
So that the ones at the other, because that won't matter at the other end. The Fresnel systems that we use, we quite often are full duplex.
Oh, okay.
You've seen those Fresnel lenses. You see the LEDs on, you see the red light on, but the receiver's on at the same time.
Okay.
So you can run a full duplex contact. But what usually happens though is you've got this massive red beam heading out that's sort of spreading out a bit, and some of that will reflect back off of dust in the atmosphere, or mist or fog or something, and you'll be hearing it in the receiver. So you might get a little bit of feedback or something.
That's a side tone in the old
But yeah, you can do full duplex. We have done full duplex contacts using the two Fresnel lenses.
7MO when he did, Joe Gelston rather. He was involved with Rex too. Made a big box.
Yeah, Rex had 60 those Cree LEDs mounted on a great big board, projecting this massive great red beam out of the sky to try and get across Bass Strait. My high power red flat light probably equals the power output of that system, but does it all in something that's only this big. And there's a certain amount of debate, from my mind. For the receiving side of the house, Fresnel lenses are good because you've got a big capture area. For the transmit side, well, I don't know whether Fresnels are really necessary. I think you're better off if you can get all your light out of a lens system and into a fairly well collimated beam. That would be just as good as a Fresnel system, I think, because it decollimates along the way anyway. I mean, it might be this wide when it leaves you, but when it gets to the other end, it's probably 100 meters wide. So, and that same thing happens to lasers. I mean, everyone's like, lasers, you've got this little dot, it's going to go over there. But at the other end, it's not a little dot anymore, because on the way through the atmosphere, it decollimates and it decoheres. So it becomes a lot. And the other problem with lasers is because of the nature of the light, Fresnel lenses don't work very well with them. So you can't use a Fresnel receiver with a laser transmitter. So that's another thing to bear in mind.
Great. Thank you.
Is there any other questions here? Oh, Mark.
One of those slides, a good idea. One of those slides mentioned daylight operation. Could you just elaborate on that? Thanks.
Daylight operations. Well, like I said, that was in German, so I was having trouble battling to understand what they were talking about. But when I found out that there was just this one ordinary lead at the transmitting end, I thought, yike. I think they must have had optical filters in their system, and they certainly had good receivers, and they had really complicated looking optical assemblies. I don't know where they got those, but they'd obviously got this down to a fine art. But I think 40 kilometers was about as far as they were going to manage. You could probably do it with infrared more easily, surprisingly enough. One thing that the infrared, the contact I had at Friedrichshafen, Klaus, he had a device that I've yet to implement on my systems. LED light output is linear with current. Once you've got over turn on knee of the diode, and provided you're not at the excessive dissipation end where it catches fire, in between there, double the current, double the light. That's the way it is. It's a straight line. What Klaus has done, using presumably an Arduino or something similar, is he built a step attenuator beacon that he switched on, and it started at full power, and then every 5 or 10 seconds, it halved the current. So it went bang, bang, bang. So 3 dB down every 5 seconds until there was virtually nothing left. And he switched this thing on, and I was listening to him, and I heard at the start, I heard him step, 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 step. And I heard him right down to the 5th level. I could still hear him in the noise. He's still there, still readable. Think about that. That's 15 dB down. It's a 1 watt lead to start with. The lead current must have been in the milliamps, and it still worked. But that was fascinating in itself. But the step attenuator idea was what impressed me. And I thought, I'm going to build one of those because it's really handy to know how well your system's performing. There's not enough room left in that little box there to incorporate that, because that's absolutely jam-packed with electronics. So I'll have to build a Mark II version with a built-in step attenuator.
I guess the infrared would be more pilot friendly.
Yeah, I've got a 3 watt infrared system as well. I built an infrared transmitter. I'm very wary of it though, because if 3 watt infrared LED focused is going to be fairly dangerous if you're not careful, I would have thought. So I'm really wary about turning it on, you know. But I do have a system. I bought a 3 watt infrared LED and built a system with it. It works. But you really need to be out in the field with an optical system so that you can see each other or line each other up, and then maybe switch over to the infrared system to see how well it works or whatever. It's the same old story. You need to know where you are, and you need to know where the other person is. The simplest way is to get there early enough and look, find some landmarks on the horizon and say, well, okay, well, that wheat silo over there, I know he's 10 degrees to the left of that. And that's where he should be. Because just waving the receiver around, scanning the horizon is a pretty hard way to go. You need to have a lot of a helping hand before you actually start trying to find the other station. Pardon?
LED in your, what's the LED in your gun?
That's just a very bright 10 millimeter LED from Descartes.
Red super bright.
Red high brightness one, only 20 or 30 milliamps or something, and they're quite bright.
Okay, thank you. Is there any questions online tonight?
Matt ZM had his hand up.
Yeah, Matt, you've got a hand up.
Yeah, thanks, guys. Tim, I'm really curious, Matt 5ZM, with your red LEDs, what kind of efficacy are you getting out of them if you're putting 30 amps in, and how many lumens are you actually able to generate in, out of some of your typical systems?
I wish I knew.
It's hard to measure.
Well, put it this way, the light coming out of the blue one will blind you. I can tell you that for sure. they're fairly efficient. You lose a bit in heat. They've got to be heat sink on the back. If you're going to run them at 35 amps, they'll get hot and you'll need to cool them down a bit. So there's a bit of loss in heat. But as to the actual light output, I guess if I go and find the data sheet, it'll tell me. I've got the data sheets on them somewhere. It should tell us how much light's coming out of them, but I can't remember what the number is.
Okay. Cool. Yeah, I was just kind of curious because some of those flat LEDs that you're playing with, you know, they're 1,000 lumens plus. So
Yeah.
they're pretty bright.
I would say, I'd say that's ballpark.
Yep.
Because, let's face it, a half decent modern projector needs to be these days 3,000 or 4,000 lumen for a good projector that can deal with a high light area. So
Yep.
you're going to need 1,000 plus for each of the three components. So yeah, I'd say that'd be a good ballpark number. I'll look it up though when I get home, just out of interest.
Yeah, I'm curious because in a past life we put 225,000 of those flat LEDs in a 1 by 1 foot matrix all over the Sydney Harbour Bridge. They're pretty bright.
They're pretty bright.
All right, thanks, Tim.
Anyone else?
And Bill, a question?
Yeah, I was wondering about on-off keying. So in terms of modulations, you mentioned pulse width modulation, but have you tried OOK?
Well, I mean, the pulse width modulation is turning the thing on and off very quickly. It turns it hard on, hard off. I mean, what other mode do you want to use? You can use it for CW, I suppose, but I don't know. Pulse width modulation works well enough. I haven't seen anyone try anything else. Any other questions?
No other questions online?
Well,
Andrew, do you want to just dip in here
board
quickly?
stiff or had enough?
Tim, would using like weak signal modes in any of your WSJT modes be advantage with this system?
Oh yeah, that's what Rex does.
Right.
That non-line of sight, call it a record because no one's done it locally. WSJT, an incarnation of a weak signal mode. That's the only way you'll do it because you're never going to hear the signal. At least I don't think you are. No, although I think in UK some guys have managed to get an audible signal, but I'm not a very sure path. I would like to be able to at least get a tone or an audible signal out of my system. Hence the reason I've gone to the extremes I have to try and leave no stone unturned. Whether it'll work, I don't know, because the problem with blue light is the scatter is the problem. I'm afraid that the beam might just get scattered far too much before it gets to a point where the receiver can see it. I don't know what that distance is. I won't know to do an experiment to find out.
When you're modulating these things at 35 amps, does the heat change the frequency of the light output?
No. No,
you don't have to spend money to keep your signal stable.
No. They stay pretty much where they're supposed to be. You just got to keep them cool. We don't run them at full power very much because there's no real point. It's way more light than you need as a general rule. Yeah. It's overkill for what we do, but it gives you plenty of scope just to start out with a very bright light if you need to. Usually wind them back because you've got to find the power for all of this as well. I mean, if it's that 35 amps has to come from somewhere. And what I tend to do, and as you saw those two power supplies that were on that modulator, is rather than when we remember the circuit diagram that was up there of the transmitter, there's a dropping resistor from the supply rail down to the lead. Now, if the lead's drawing 35 amps and there's only 2 volts across the lead, and there might be a volt across the sense resistor, the other 8 or 9 volts is across that dropping resistor. Simple Ohm's law tells you that 8 or 9 volts with 35 amps is an awful lot of energy that's in this dropping resistor. So no, that's why I bring the voltage down to just enough voltage to power the lead and the sense resistor. So, and of course, because it's a buck boost device, you might only be using 4 volts at 30 amps, 120 watts. At least you're not drawing that 30 amps out of your main supply. You might only be drawing 10 amps maximum, because the buck boost regulators put it into a ballpark that's more convenient to use. But like I said, that was more of an experiment than anything, because you don't really need it. You don't really need that level of power. I don't use the big one very much at all. I mainly use the 20 amp one. We only run that with an idling current of just a few amps. There's plenty enough light. As we just had that discussion on brightness of these things, there's energy to burn. So you don't need the massive power, but except for an online or site thing. With an online or site thing, yeah, you probably want all you can get. And I'll probably run the blue LED at full power just to see what happens. And that'll be a sight to behold as well. So we'll see.
Okay, well, I think we'll just wrap it up there. Feel free, if you're in the hall here, feel free to speak to Tim during the break. I'm sure there's be more than happy to answer any other questions or pass on any other details. And I'd just like to thank Tim very much for this evening, for the talk. I think everyone got something out of it here in the hall and also online. So thank you very much, Tim. We'll have a short break, about 10 minutes, meet back a bit after 9:05.